Hello, my name is Jack Burns from the University of Colorado, and I'm here today to talk about NASA's first delivery of radio science payloads to the surface of the moon using a new program called the Lunar Payload Services Landers. To put this into perspective, I'm showing this chart from NASA that in the top portion of the chart, the swish going across represents the human side of the Artemis program, which is NASA's plans for new journeys to the moon. Artemis consists of the Orion capsule and the SLS rocket. Its first test launch will be later this year, leading by the middle of the decade to a planned first human landing on the surface of the moon in the 21st century. Simultaneously, NASA's Science Mission Directorate has undertaken a new program involving unmanned landers to deliver science payloads to the moon using what's called the Commercial Lunar Payload Services, or CLPS program for short. CLPS is shown here, described in a little bit more detail. The program is to be rapid acquisition and rapid delivery of payloads to the surface of the moon. Unlike in the past, NASA is actually buying services from commercial companies to do this. The first two such launches are scheduled for later this year by two companies, one called Astrobotic in Pittsburgh, and the other is Intuitive Machines out of Houston. And I'll be talking more about Intuitive Machines because it is delivering our radio science payload. That payload is called ROLS's, which is defined on this slide here. The principal investigator is my colleague Bob MacDowall at the NASA Goddard Space Flight Center, and then Bill Farrell and I are two of the lead scientists. ROLS's is derived from some high heritage for NASA heliophysics missions. The payload is relatively simple. Four 2.5-meter monopole antennas forming cross dipole antennas, and a radio spectrometer with two bands that extends from 10 kilohertz up to 30 megahertz. And as I mentioned before, it will fly on the Intuitive Machines lander. So let me show you a little video, just a clip of a video from Intuitive Machines on what we hope will look like later this year, the landing of the Nova-C lander onto the surface of the moon carrying ROLS's.
Acquisition of signal and lunar orbit insertion complete.
HDA scanning in progress. Safe sites found.
Prepare for landing.
We certainly have our fingers crossed that the landing will look that smooth. One of the things that will be really exciting about this landing is it'll have a series of cameras on board the lander to record the landing in real time, and also will eject several CubeSats that will take imaging from beyond the lander as the lander is descending to the surface. So the science goals for ROLS's are shown here. A lot of these goals involve plasmas. In particular looking at the local ionosphere, the interaction between the solar wind and the regolith, the so-called photoelectron sheath. Also to do observations of the sun type 2 and type 3 bursts, if any occurred during the roughly 10-day mission that we have to measure the galactic spectrum, which is not well measured below 30 megahertz. And to also measure the local electromagnetic environment, including the lander for use in future missions. We're also very interested for future missions in looking at the electromagnetic interaction of the antenna beam with the lunar surface. If you look here at this example in which we have modeled using the CST Microwave Studio electromagnetics simulator, the Rolls' dipole beam, both in a vacuum and on the lunar surface. In both cases, we include the lander because that's important as well. And you can see that in a vacuum in the on the left-hand side, looking at the E-plane, for example, it's as expected, more or less in 3D. It would be a donut shape, relatively smooth as a function of angle. And then when you look at when it's on the regolith, however, that interaction with the regolith has in fact distorted the radio beam. One can use this distortion to reverse engineer and infer the subsurface properties of the regolith. So Rolls is scheduled to be delivered to the moon later this year on the Intuitive Machines. I had an opportunity to visit Intuitive Machines in Houston just a couple of months ago, and on the left-hand side shows a full-scale model of the lander, and on the right-hand side is the NOVA lander control room, which is set and ready to go. So we are very anxious and excited for that first launch a little bit later this year. Our second mission, which will occur later in the decade, is called LUCI. And LUCI stands for Lunar Surface Electromagnetics Experiment. The PI is Stuart Bale from UC Berkeley. And this mission is going to go to the far side and meant to take observations in a very different environment. LUCI, like Rolls', was selected early on, about 3 years ago, as part of the CLIPS program. Recently, though, in this last 6 months or so, it has been split into two payloads, what we're calling a LUCI Light that will go to the South Pole Aitken Basin on the far side and do the plasma component of the experiment, the counterpart of what I was just mentioning for Rolls'. And then an exciting new version, LUCI Night, that will also go to the far side in 2025. And with the new collaboration from the U.S. Department of Energy, we can carry enough batteries on board to be able to operate for the first time at night. And this will operate in between roughly 1 and 100 megahertz for radio astronomy purposes. So the U.S. Astrophysics Decadal Survey, which came out a few months ago, identified the dark ages as the discovery area for cosmology. And LUCI will allow us to begin a Pathfinder experiment in radio cosmology and specifically in the dark ages. You see on this slide a cartoon picture of the evolution of the universe from the Big Bang on the left to today's universe on the right. It's logarithmic in time. And beginning over with when the CMB appears, this is the epoch of recombination. This is when the first atoms of neutral hydrogen form. From this point on, the intergalactic medium is filled with neutral hydrogen. And this is called the dark ages initially because there are actually no stars or galaxies. And then this leads eventually into the cosmic dawn with the formation of the first stars. COBE on the one side is able to sample just before the dark ages begin and JWST and Hubble are going to be able to poke their nose into the later era of the cosmic dawn when those stars begin to form. But really, we have a resulting large gap that will exist, that does exist between the dark ages and the cosmic dawn, that can be filled, though, recognizing that we can utilize the highly redshifted 21 centimeter signal from neutral hydrogen to sample the structures during this time period. With experiments like Lucy, we are going to go after the 21 centimeter global signal from this dark ages and cosmic dawn. On the lower left, you see this plot model spectra of the radio brightness temperature measured against the radio background versus frequency. The dash curve in here represents a standard model, so standard star formation and adiabatic cooling. And in the color curves represent parametric models that involve additional cooling, excess cooling, possibly the result of scattering by partially charged dark matter with baryons that has been speculated as a result of these edges results, which are still quite controversial. And one can see that the models break apart very nicely in the dark ages. So being able to sample that time period is going to be very exciting. This, even from the moon, though, is a very challenging experiment. One cannot do what we usually do in radio astronomy, and that is observe against a foreground and subtract out that foreground, because that foreground is 4 to 6 orders of magnitude. One needs to use more sophisticated techniques, and our group at Colorado has developed a pipeline involving pattern recognition and Bayesian inference that allows us to do simultaneous fitting of the systematics along with the signal. We start off with our observational strategy that involves both polarization and time-dependent observations to be able to separate the foreground from the signal. We then use a series of training sets from a combination of models and measurements of the radio beam, the receiver, the sky, and 21 centimeter models, and use SVD, singular value decomposition, to sample these and to fit the spectrum with well-defined errors. And then finally, we use an MCMC code, a Markov chain Monte Carlo code, to extract physical parameters such as information on the turning point frequency that will tell us when the first stars and galaxies turn on, and also if, for example, we're looking at differentiating warm and cold dark matter, where those minima in the spectra will be that will separate those two models. We're still in the design phase for Lucy. So far, our team is using stacer antennas with heritage derived from stereo and waves. One of the novelties here is we're looking at putting the antennas on a turntable and rotating it, and then using a signal beacon, a radio signal beacon from a communications satellite to map out the radio beam. I mentioned before that we're carrying batteries, and so when the lander lands, it turns off, and so we will be isolated from that lander, and we've worked very hard to minimize the electromagnetic interference from that environment. This is part of what we're attempting to study on the far side, see how well we can do in this kind of environment. So the final summary or final thoughts that I want to offer is that NASA's CLIPS program is exciting, but it is a high risk, high reward program because of the rapid nature and the commercial nature. There is some risk of failure. When it is successful, eventually this is going to be a game changer because it's going to allow regular access to the lunar surface. The first set of payloads, Rolls and Lucy, will move us in the direction of doing the cosmology, 21 centimeter cosmology from the moon, and also help us prepare for next generation of instruments, an array on the far side, which we call, as you see here, far side. And this was the result of a study that we conducted with JPL to deploy 256 dipole antennas. Thank you.